So for the next presentation, we're going to talk about the use of artificial intelligence to detect industrial cybersecurity anomalies. So we'll hear from Thomas Anglade, who's the head of AI for the company Sekiot, is going to come to talk to you about this solution. Over to you, Thomas. Hello, everybody. I have, well, a quarter of an hour to try and explain to you what we are doing in AI. I'm going to try to do this efficiently and effectively. So to talk to you about how we use artificial intelligence to detect anomalies related to cybersecurity, how we identify anomalies, abnormal behavior, surprising behavior in industrial networks. So CFI is a mapping solution, analysis of vulnerability and detection of threats, which is 100% French and which works on industrial systems. So the purpose here for a quarter of an hour is to tell you a little bit about how we worked in terms of R&D to have a relevant what are the major principles that we based our work on? What are the challenges that we encountered? So a quick introduction to tell you a little bit about how we did this and why we use AI in cyber. Then the major principles, the challenges to implement these systems and what we're working on a daily basis in terms of R&D. The first question is, why do we use AI in industrial cybersecurity? The whole point is to have something that is more efficient and effective than just implementing rules. If you look at flows, like a flow, which is a communication history between two machines, so the number of packets exchanged over time, here you can see that there is a pattern. Clearly there's a pattern. There's it's regular, it's cyclic. There are things that are reproduced over time. And if you zoom in, well, I think you can see a little bit. If you zoom in on the history, the number of packets exchanged between two machines, you can see that there are regular things, but you'd have trouble monitoring that with deterministic rules and threshold notions. That's why we're going to use artificial intelligence to monitor these flows that have a variability portion. Another example that we have here is another flow that we can see here in orange. If we wanted to monitor this flow, monitoring it over time and detect deviations from those exchanges between two machines, we'd have to define the frequency of the peaks, the length of the plateaus, define also all the possible variations. And we'd have trouble doing that, or it would require too many rules, and that's why we're going to do it with machine learning. It's to just explain to you what we're doing and how we're using machine learning. Having said that, the major principles and the functioning of an artificial intelligence in cybersecurity for detection is to have a learning phase where we're going to collect data. That is the whole phase you can see on the left-hand side of the vertical red line. So we're collecting data, we look at the patterns. The algorithm learns these patterns, learns these time series, and then once that learning process is over, we're going to move on to the inference phase. In the inference phase, what we do is we look at the flow, and we're going to ask the algorithm every time to tell us if this flow is consistent with what it learned. If it is not the case, then there's an anomaly. So regarding machine learning, for those who know about it, this is an algorithmic task which is prediction or forecasting or a temporal series. So we're going to ask the algorithm to predict the next values, compare those values with what happens, and if there's too much of a difference, if there's too much of a gap, if it's too different from what was learned, then there is an anomaly and troubleshooting needs to be implemented. That's what we're trying to do. So what are the challenges that we have when we want to implement this on industrial systems? The first challenge is to define what can be learned. Well, it's quite logical, it's trivial, but you cannot predict something that is random. If you look at this flow between two machines over time, there is clearly something happening, but it's quite random. So apart from having a threshold, so low threshold, high threshold, and say, well, if it's outside this, we troubleshoot because there's an anomaly. And in this case, the AI isn't going to help us very much because the way in which we translate it ourselves is to say that we have a learnability score which is close to 0. That's something that we're going to monitor with mapping rules or Sigma rules, but other deterministic techniques in our solutions. But AI will not be able to help us in this case. However, on the other hand, here is another flow which is constant, always constant. It's another communication flow between two machines, a packet per second, always constant over time. Here, on the other hand, the learnability score is close to 100%. Here you can have a rule. If what I observe is different, there'll be an alert, but this perhaps, and its learnability score is too high to have interesting patterns. So the idea here is to focus on the flows that are between 0 and 100, where we can see that there are cycles, there's regularity, we can learn something, and we can monitor that with machine learning. The second challenge that we have is the personalized or customized learning. The objective with the AI is to calibrate models within each models within each network. So we're going to monitor what we call the features, the metrics. We saw, for example, the number of packets per second. We saw that before. We can think of other features that are very interesting to look at in industry, intersession duration or minimum period between two packets. So we're going to calculate these features in terms of consistency. For example, the number of packets per second. That can be relevant for some machines, but not for others. We can define a number of features that can be calculated consistently with the mapping and the role of the machines within the network. And we can also ensure that the expert user has a role in this process to select the features. He can say, well, I know my network and the intersession time is relevant for this flow, but not for that flow. And then our challenge is to do customized or personalized learning. So once we have defined the features that we want to monitor, the metrics we want to look at, and what link we're going to use to look at them, we are then going to train the algorithms so that this is done automatically in each network. So we don't have a pre-training session. There's no pre-trained algorithm. It's not transfer learning. In fact, automatically we will collect all the data on the learning history and then train the models on that history. So the challenge for us, what we worked on in R&D and what it's done in our solution, is to automate all those steps with all the questions that go with that, collecting the data automatically, calculating the features that are going to be an input for the machine learning algorithms. As we saw earlier, define what can be learned. In other words, give a score to each of the flows to say this is relevant, there's regularity, there's a cyclic approach, there's frequency. So my user has told me this is valuable information for our profession, so we can use it for machine learning. Then the fourth phase is to calibrate algorithms. So once I have my data, my history of learning, I can automatically calibrate my algorithms. I have many questions, of course, that come up here, of course, related to performance, related to effectiveness, computational effectiveness, how many links must I monitor. I cannot have a network of neurons per link, so I need to have something that's effective in terms of performance and resources. And once I finish that calibration phase, then I just need to choose the thresholds. So what is the tolerance that I want to have for my algorithm? From what gap compared to what is predicted and what is observed? When will there be an alert? When will there be an anomaly identified with a possible input of from users who have expertise? And once I've done that, well, then I can really move into alert mode and move into troubleshooting mode. The last point, which is crucial for us, is explainability. This is something that we talk a lot about in artificial intelligence, so provide explainable alerts. We don't want AI to be a black box, so we focused on algorithms that have a form of explainability, so we're able to understand why they made that decision. For us, the challenge in terms of explainability and the way we solved it is to say that explainability is 2 criteria. There's the first criteria, which is the technical and algorithmic explainability, so to answer the question, why did the AI engine go off? And give a visual interpretation of that. So here you can see it on the left-hand side. I have a flow that is a sequence of events over time, and I have to be able at all times when I have alert to visually interpret the behavior that is beyond the tolerance threshold that we'd identified. So that, of course, impacts the choice of algorithms, their openness on neuron networks or complicated models. You can have it, but it's what we choose is algorithms that allow us to completely understand what happened. The second point is what we call the professional-based or explainability. So here it's the business aspect. So to say for the business explainability, in what context was the alert identified? We want to be able to explain, well, the phase between the machine learning, the artificial intelligence, the mapping, and the analytics engine. So that is what is going to define the flows, describe the flows and the interactions between the machines and the network. In terms of contextualization, what we also want to be able to do is compare the link that, where the alert, it's to contextualize it is in the mapping. So what is the state of the rest of the network when that alert, when that system that came up. So thank you very much for your attention. We are doing demonstrations of all of this on stand E19. On E19, we can show you the algorithms, how they detect attacks, and how we can go into more detail and understand what happened. Thank you. If there are any questions, please don't hesitate. Thank you for that brilliant explanation.